right, take it away, Sally.
Great, thank you, Hazel. So my name is Sally McFarlane. I'm a program manager at the U.S. Department of Energy Office of Science, and I am one of the co-leads of the Monitoring, Observing, Modeling, and Prediction, or MOMP, Foundational Activity Team. And along with my co-leads, David Allen from the Arctic Research Plan, the MOMP Foundational Activity Team works to coordinate activities and communities of practice that bring together Arctic modeling, observing, monitoring, and prediction to advance Arctic research. And so we developed the idea for this meeting because, as I'm sure many of you are well aware, that the development of artificial intelligence, or AI, and machine learning provides really promising pathways for a variety of applications in Arctic modeling and observational research. As the Arctic is such a rapidly changing region, there's also concerns about whether AI techniques can extrapolate beyond the currently observed conditions to project future states of the Arctic. So we've organized, or we are hoping to organize, a whole series on AI that will explore applications of AI in Arctic research and discuss these areas of promise, as well as potential limitations and perhaps cautionary tales we should all be aware of in both modeling and observational research landscape. So today is our first webinar in the series, and we have two speakers. WenWen Li from Arizona State University is going to present highlights from her work using AI to extract features from satellite images with applications for permafrost thaw and sea ice. And then Will Gregory from Princeton University is going to present highlights from his work using AI to improve sea ice and ocean models. And I think both speakers are going to discuss their thoughts on the areas of highest promise and potential limitations as well. And then we're also interested in sharing AI resources and tools with the community. So we have developed a Google document, which Hazel will post a link to in the chat if she hasn't already, for the community to share additional AI resources, tools, and publications, ideas for future topics for the webinar series, and any follow-up actions that you want the MOMP team or the community to consider. So you're welcome to add ideas either now or during the discussion period. So I'm going to briefly introduce each speaker before their talk. They'll give their presentation, then we'll have a couple of minutes after each talk for just clarification questions directly related to their talk, and then we'll do the open discussion after both talks. So we'll go ahead and get started. So as I mentioned, our first speaker, Dr. WenWen Li, is a professor of geospatial data science in the School of Geographical Sciences and Urban Planning at Arizona State University. She directs both the Cyber Infrastructure and Computational Intelligence Lab and the Spatial Analysis Research Center. And her research focuses on cyber infrastructure, big data, and geospatial artificial intelligence with applications in data and computation-intensive environmental and social sciences, particularly in addressing environmental change in the Arctic. And WenWen is quite accomplished. She is a recipient of the NSF Career Award and the Mid-Career Advancement Award, and she is a fellow of both the American Association of Geographers and the University Consortium of Geographic Information Science. So we're very excited to have WenWen speak to us today, and you can see her title right there. So please go ahead.
Yeah, thank you, Sally, for the invitation and the very nice introduction. Good morning and good afternoon, everyone. So today I want to introduce like my past decades of research of like AI in Arctic science and also big data in Arctic science is where I started of combining information science with Arctic science. And I would like to discuss two studies that we are currently working on. One is on the permafrost feature detection, and the other is on the sea ice concentration forecasting. So as I mentioned, I think AI in Arctic science has a lot of potentials to address the challenges in the data lifecycle, from making the Arctic data more discoverable to enhance the semantic search of the data, to the integration of diverse data set from different Arctic organizations, and also to the visualization of the polar data, to the intelligent analytics of the data. So in fact, when I get started to work on the Arctic project is to develop the Polar Hub, which is an self-funded project. So I started this when I was a PhD student. I got involved in building the Arctic spatial data infrastructure when I found, oh, there are so many data that is hosted by different mapping agencies across different countries. So making the discovery and management of the Arctic data very challenging. So, and when I built the spatial data infrastructure, and I surprisingly found the people from different countries, they're all very supportive and very collaborative in terms of sharing their data broadly to enhance and advance Arctic research. I guess that is how I got very interested in the Arctic research, and I still am very interested in the Arctic research. And another project that I have done in the earlier years of my study is to develop the visualization tools, the real-time visualization tools to visualize the Arctic atmosphere. So because when I was invited to an Arctic workshop focusing on the visualization, so we know that a lot of these 2D map-based visualization, if we are looking at the Earth, other regions, then polar region is gone. So that motivated me to develop a new tools that is not just a 3D, that so we can view the Arctic regions as a whole, and also multidimensional, like 4D visualization, where we not only captures the Earth's atmosphere on the Earth's surface, but also attend to the Earth's atmosphere. So as you can see here, this is an example of showing the temperature over Greenland in different months, from the winter season to the summer season. And we can also visualize like the Earth's wind or the ocean current. So in a vector field visualization, or we can combine like the vertical profile visualization with a volume rendering to just look at the different patterns within the Arctic atmosphere. And these two projects like deepens my understanding of how we can apply advanced cyber infrastructure technology to support Arctic science. And once we make this data more discoverable, and once we were able to visualize this big data, I think one of the critical areas is how we can make use of this big data we have to generate new knowledge or more intelligence. So that comes to an area of what I have been working on in the past several years is GeoAI, because on the one hand, we have vast amount of Earth observation data from remote sensing, satellite imagery, from numerical simulation models, and from field observations. How can we better utilize them in order to advance our understanding of the changing Arctic system? And the one project that I have been working on very intensively is for mapping Arctic permafrost thaw. So this is within the Arctic, the Permafrost Discovery Gateway project, where our goal is to monitor the environmental changes and also respond to emerging crises by leveraging big data, advanced technologies like cyber infrastructure and AI. And this Permafrost Discovery Gateway was originally funded by the National Science Foundation, and recently we received a $5 million research grant from google.org, where we are trying to substantially expand the existing capabilities to use AI to track permafrost thaw in near real time. So we can take a pulse on the changing Arctic landscape and also to inform climate actions. And this project is led by Woodwell Climate Research Center with Dr. Anna Liujidao as a PI, and with participating organizations from like an international perspective. And here is the big data processing pipeline that we have built. So first of all, one of the major data source we are using is the big satellite imagery from Polar Geospatial Center. And we are leveraging the high performance computing resources from NSF and and also commercial cloud like Google Cloud to support the pan-Arctic level big data analysis and generation. And the GeoAI serves as the analytical core that enables the intelligent and the scalable mapping and generation of big data from our satellite imagery. And one of the permafrost features that we are trying to map is called the retrogressive thaw slumps. So this is like a landslide kind of feature, and it forms when permafrost started to thaw and causing the ground to collapse. So as you can see, there is a like a dent in these areas, and when a permafrost thaw when a retrogressive thaw slumps forms, it also causes like interruptions in the vegetation. And these features are very important indicators of Arctic warming and climate change in the Arctic. And so when we develop AI capabilities, one of the methods that we have developed is leveraging multimodal data for thaw slump mapping. So here are several different data sources like optical image, so high resolution satellite imagery from Maxar. So as the arrow pointed, you can see a dent in this area. So that is a thaw slump features. And we are also introducing additional data source like the NDVI, the normalized difference vegetation index. So you can see in the thaw slump areas, the vegetation is in red. So that means interruption in the vegetation. And when the thaw slump feature forms, because it's a landslide, it always causes like the elevation changes. So we also introduced the Arctic DM data, the digital elevation model data into this multimodal modeling process. And with AI, though I didn't have the details about the methodology, but you can take a look at our papers to refer to more details. So here is just an example of using our multimodal GeoAI models for doing the thaw slump segmentation, what the result looks like. So the red mask shows the ground truth labels, which are annotated by Arctic researchers. And then we can see the model's prediction in blue. By the way, this image seen is from like bay areas in Greenland. So when we use the RGB image alone, like the optical image alone, the model is only able to segment one of these features. And when we are adding additional source like RGB image and also the vegetation index, the model is able to perform better. And then when we were gradually adding like again additional, this is near infrared. So I introduced that the elevation data is important for identifying this kind of thaw slump features, but in our experiments, we didn't find that adding the DM giving us that the vertical differences that we are looking at. So instead, we add another data layer, which is near infrared data, which can give us the soil type information better. So this result shows when we combine this multi-source data, the GeoAI model is able to predict like 3 of the 4 labeled thaw slumps. So we can see like when we are gradually fusing the multi-source information, the model is going to perform better. However, because thaw slump features are very difficult, a challenging feature to detect, there are still ways for us to further improve the model prediction and its capability. And besides this, permafrost thaw research, we are also interested in like the sea ice research. I understand that the permafrost group, like the land group, the sea ice are kind of an independent research group for Arctic research, but they are two very important topics. So that motivated us to take a look at what is the role and what is the progress of leveraging AI and deep learning for Arctic sea ice remote sensing research. So with colleagues, we developed this review paper to review the current progress and also the remaining challenges in this area. So what we did is we found there are already quite a lot of this integration of AI in Arctic sea ice research, mainly in these 6 different areas for sea ice lead detection, sea ice thickness estimation, sea ice concentration estimation, and sea ice concentration or extent forecasting, the motion estimation, and also the type classification. So giving that overview, we want to dive into a challenging problems of seeing how AI is doing in terms of the sea ice extent forecasting to forecast the change of sea ice extent on a seasonal basis. So what motivated our research is this, I think, is a pioneering research of leveraging deep learning to forecasting sea ice. This is led by an author from UK. So when we do literature review, it was quite surprising that there are fewer of this kind of work in the US-based institutions. So we decided to give it a try, inspired by this research. So in this previous work, what they did use a deep learning model, which is actually a quite popular models, although the problem is on doing sea ice forecasting, but they are actually using an image analysis model. So this model is called UNet. It's called UNet because, it's a UNet shape.
Just a couple more minutes.
Okay. Yeah, it has a UNet shape. So for your input, like RGB images, and then what it can get is a segmentation result, which can segment the different objects or features within the image. And then in this, how can we adapt this image analysis model to forecasting problems? So what they did, the authors did is very interesting work is, okay, so we are going to stack this time series of input variables about sea ice concentration, temperature anomaly, like in the past 3 or 6 months, or even a year as channels as input. And then the output, if we are going to predict the next 6 months of sea ice extent, we are just ask the model to predict like the 6 output within the 6 channels. So they were able to address these forecasting problems by adapting the input and output to use an image analysis model to achieve that goal. So we think that we can kind of develop a stronger model. So this is our design of transformer-based model where we put a lot of efforts in address the temporal heterogeneity in the variables, because some of the variables, they may have 12 months long, and some of the variables may only have 3 months of impact to the sea ice extent changes. So these are our model results. As you can see, our StepNet model has performed the best in comparison to the SNet, which is a paper I have shown published in the Nature Communications, and it works better for the 2nd month to the 6 months prediction than the CIS5 numerical simulation models. But the 1st month is still not as good because this kind of numerical model is very strong in terms of the near-term prediction. Here are some of the visualization. You can see this is prediction in 1 month, 3 months, and 6 months. So 1 month prediction definitely is the most accurate. And we have a lot of results discussed in this paper. If you are interested, please feel free to take a look. And some of the lessons learned from our result in our analysis in permafrost thaw and also the sea ice forecasting is AI could play an important role in Arctic research. And another thing that we found very important is the data scientists and Arctic scientists need to work closely together, because from us alone, we can analyze very complex data, we can develop the models, but it's difficult for us to explain the results from the scientific perspective. And also complex models are not necessarily better. In our Arctic sea ice forecasting research, we develop quite complex models, but as you can see, compared to the SNet model, that the first sea ice forecasting model, the performance advantage is actually just marginal. So there are also other challenges of applying AI in earth science. So I have put this reference as a provide some of my own perspectives and also some related work. Okay, thank you so much.
Great, thank you so much. So we have just one clarification in the question in the chat. Lauren wanted to know, did you say that the digital elevation model was not used in your final permafrost thaw model?
Yes, our assumption is it will become very helpful, but when we try to use the Arctic DM data, both in 2-meter resolution and 0.5-meter resolution, we didn't find it as helpful as other band or data sources. So in our final model building, we didn't use the Arctic DM. Analyzing the reason, we feel that the vertical accuracy of the DM data is very important. When it couldn't capture the subtle differences in the elevation changes, or there is a misalignment in terms of when the thaw zone forms. So if the DM is captured before that, it cannot capture the feature. So yeah, so in the end, we didn't use RTDM.
Great, thank you. Okay, we're going to move on to our second speaker, and then again, we'll have more general discussion at the end. So our next speaker, Dr. Will Gregory, is a postdoctoral researcher at Princeton University based at NOAA's Geophysical Fluid Dynamics Laboratory. Prior to this, he received his PhD in polar climate and machine learning from University College London. His research combines large-scale observational data, models, and AI to better understand the polar climate system. His past work includes some of the earliest work on data-driven sea ice forecasting, as well as using AI to reduce the latency of sea ice thickness observations from satellites. At Princeton, he has been developing a new hybrid sea ice model, which uses AI to improve the fidelity of numerical simulations. So go ahead, Will.
All right, thank you. Yeah, it's great to be here. I'm always excited to join meetings where we can focus on polar climate and sea ice. So yeah, I just wanted to share some of my perspectives of applying AI techniques to sea ice, various aspects of sea ice research over the last few years. So I should say I'm part of this international kind of collaboration effort, M² Lines here, which is a project funded by Schmidt Sciences, where we're looking to use AI tools to develop the sort of next generation of hybrid climate model components. So we're focusing on atmosphere, ocean, and sea ice in this project. And Schmidt Sciences is also funding this other project, SACIP, Scale Aware Sea Ice Project, which is based out of Europe, who are specifically targeting sea ice problems. And they're also looking at AI tools there as well. So if you're interested in a lot of this work and other things, specifically sea ice, I'd say check out these two projects. So I kind of wanted to frame this talk around the area of sea ice prediction. That's what I spend a lot of my time thinking about. And so really, I kind of simplify the problem and think about what do we need to make reliable predictions of the future. And number one is a good prediction model. So, if I know the sea ice conditions now, my good prediction model should be able to give me a reliable estimate of the sea ice conditions at some point in the future. And we can make some choices about what sort of model we want to use. We could rely on indigenous knowledge if we're thinking about looking at local changes in sea ice conditions over a specific time frame. We could use AI models and climate models and a combination of AI and climate models called hybrid models. So as I say, we'll choose a model depending on what sort of problem we're looking at. If we want to focus on like global scale changes across multiple decades, climate models have been the kind of typical tool of choice for that. AI models are really making advances and the short timescales, sort of days to seasonal timescales. But I think the research is growing all the time, and they're really pushing the boundaries and going to longer timescales. And also, we need good data to be able to both train our AI models and also calibrate our climate models on past historical data and initialize these climate models to make accurate predictions. So these two combinations of things I see is really pivotal for making good estimates of how sea ice is going to change across different timescales. And I'm going to touch on both of these things throughout the talk. So for sea ice prediction, I started thinking about this during my PhD and looked at this plot a lot. And this is tracking the sea ice changes in summer in the Arctic. This is the September sea ice extent, kind of I guess famous time series among the sea ice community. We can see the strong downward trend due to climate change. But on top of this trend, there's a lot of interannual variability. We can see these year-to-year changes, and a lot of people in the community are working hard to try and see if we can predict these interannual variations on different timescales. And this has really been a huge effort since 2008 through this sea ice prediction network. This is a kind of US interagency funded effort, which really gathers people across the community to submit forecasts every year of the sea ice conditions in September. And these forecasts range from statistical and AI models to fully coupled climate models. So in my PhD, I was looking at whether we can actually apply some more sophisticated statistical or machine learning approaches to forecast sea ice. At that time, it was really dynamical fully coupled models were kind of the main models submitted to the sea ice prediction network, but there was also a growing effort of statistical models, but these were typically based on simple sort of linear fits or linear regression techniques. So one thing I was looking at was how we can use machine learning to both identify patterns of variability within climate data set. This picture on the right is showing how sea ice varies according to if we construct a kind of graph representation of sea ice. We can see here where we form nodes of a network where red links show that regions kind of co-vary together, where if one region experiences higher sea ice conditions, so will another, and vice versa. And I wanted to see if we could use this technique to forecast September sea ice conditions on seasonal timescales. So we could construct maps of these sea ice networks a few months in advance, so maybe in July, and we could see if we could use that information to inform sea ice forecasts of September. And we found that we could predict this, these interannual variations with pretty high skill. So we were really happy with that at the time. And there was a recent intercomparison study led by Mitch Bushak out of NOAA looking at comparing all of these forecasts that were submitted to SIPN over the years with both looking at statistical and numerical forecast skill. And here, anomaly correlation coefficient is basically how close we match this observed sea ice extent time series. A 1 would be a perfect forecast, looking at 3 months ahead of time. And our model there is highlighted in black. So still doing pretty well, even though it's 5 years old as a technique now. So forecasting sea ice extent, doesn't really, that was a big effort 5-6 years ago, but really it's not that useful for people who actually want to use sea ice forecasts. Just to say, oh, I've got 10 million square kilometers of sea ice in the Arctic or whatever, that's not particularly useful. So ultimately we want to incorporate some spatial information, and deep learning has really kind of made significant strides in recent years, and WenWen already highlighted this work by Tom Anderson and developing this IceNet deep learning approach. And this was really kind of some seminal work in terms of making deep learning advances for sea ice prediction. So I won't touch on that because it's already been covered. But just to say, in recent years, these techniques have become more and more complex, and the networks are becoming deeper and bigger with more weights, and that's really kind of steering their ability to start to lead the pack in terms of their ability to make spatial sea ice predictions on seasonal timescales. And I'm pretty interested in climate models these days, and trying to understand how they can contribute to the sea ice prediction problem on different timescales, certainly. And climate models are typically configured at different spatial resolutions depending on the problem we're going after. A typical resolution is a 1 degree model, shown on the left here, which is typically used for long time scale, things like climate projections. We can have finer resolutions like a 1/4 degree, which start to resolve, leads in the sea ice, which are used less often for longer time scale predictions. So for the last few years, I've been trying to figure out, how reliable these climate models for different applications, and whether we can improve them. So this is just a quick summary of how climate models are doing at simulating Arctic sea ice. This is the kind of how they do it, the seasonal cycle in the Arctic. Each individual gray line is an individual model from the CMIP6 project. So we can see that individual models generally show a lot of bias relative to the observations. Some have too much sea ice, some have too little. If we average across all of the models, they do pretty well, but each individual model is biased. And this bias also, leads to uncertainty in future projections. If we look at future projections from CMIP6 models for Arctic sea ice in summer, you know, thinking about when will the Arctic become ice-free there's a lot of uncertainty surrounding that. And yes, a lot of that uncertainty is driven by how we're going to change our emissions going forward, but a lot of it actually comes from the differences in the representation of physics within these models. So what we call sort of model physics errors. And this uncertainty really, you know, limits our ability to understand how things are going to change in the Arctic in the future. You know, how will sea ice retreat impact coastal erosion rates and impact extreme weather and so on. So how can AI come to the rescue here, or at least kind of help improve climate model or reduce climate model errors? So part of M² Lines, this project I mentioned at the start, we're really trying to develop this new paradigm of hybrid climate models where we can, in certain cases, use observations to inform different aspects of the physical processes that we're trying to target within the model. So we could say like, okay, I have an observation of a certain process. How can I use that information from the observations to improve that representation within the model? And then we're doing that by machine learning, and then we integrate that machine learning model into the climate model to reach this hybrid model. So some work going on from some colleagues in Europe is trying to improve the representation of melt ponds. So here's a plot showing the typical grid resolution in the Arctic of a numerical climate model around 50 kilometers. We can see inside that there's a lot of heterogeneity in sea ice. You know, we see individual ice flows, and these areas of darker color on the ice flows are actually melt ponds on the sea ice. And these are these pools of surface water which have a dramatic impact on the sea ice thermodynamics and the seasonal evolution of sea ice. And you can see for scale here that some of these melt ponds are small, but ultimately in the summer they kind of contribute to a huge surface area and really impact the surface albedo properties. So we need to get these processes right in climate models, but because our grid boxes are so large, we can't actually explicitly represent them. So we have to what we call parameterize them. So some work going on from colleague Simon Driscoll over in Europe is trying to emulate these melt ponds so that we can basically have an AI model which predicts the surface fraction of a grid cell which is going to be covered in melt ponds, and that should kind of help represent these this thermodynamics better in the models. Something that I've been doing is actually just looking at whether we can actually predict the model errors themselves. So can we use some observations to tell us how wrong our climate model is here in the case of sea ice concentration, and can we learn some state-dependent representation of that error? So can we use information from the model's own climate states to predict its own sea ice errors? And here we find that if we put that neural network back into the model and rerun a simulation, we find that our hybrid model has lower error than the original climate model. So here red means the model has too much sea ice. The contour here is the observed ice edge. So in the climate model, this is in summer, we have too much sea ice, kind of equatorward. And then we reduce a lot of these errors with this hybrid model here. And this average is a kind of a long-term average of the simulation, showing that we've reduced the RMSE of the simulation with this hybrid modeling approach. And this is some recent work where we've actually put this, the last one was, I was showing that in the context of a prescribed data atmosphere where we're telling the model what the atmosphere is. So it's not a real kind of forward forecast. So here we've applied this to GFDL's operational seasonal to decadal prediction model. This is called SPEAR. This is for the Antarctic, but similar stories could be applied to the Arctic. Here we're applying this in a real sea ice forecast. We initialize the model in March and we let the model run freely over the course of the next year. And we can see that our hybrid model is tracking the observed sea ice extent, or improving the representation of the sea ice extent within the model over the course of this 1 year. So this is a new study that's in review at the minute. So that's kind of a very rapid overview of how we can use AI to kind of help the problem of climate modeling, and now I'm going to touch on the problem of data. So a lot of you are probably aware that sea ice thickness has been really revolutionary in our understanding of sea ice and our ability to measure it from space using altimetry data. And we do this by measuring the elevation of the sea ice, and then we compute this freeboard, which is the height of the sea ice above the ocean. And we use some principles to kind of extract the thickness from that. Historically, these observations have only been available in the winter season, and recent developments using deep learning have allowed us to actually extend this record into the summer. So we now have a full year-round picture of how sea ice thickness varies in the Arctic. And we've had these observations going back to 2011. But one of the limitations of these altimetry data are that they're inherently sparse on short time scales. So they collect data along these narrow tracks. And then we can see this animation here showing that over the course of a month, we start to fill in the Arctic. But that means we have to wait a whole month to basically fill the Arctic with sea ice thickness observations. So understanding how thickness changes on short timescales is difficult.
And
So I've been
2 more minutes, Will.
Great. So yeah, I've been looking into how we can use AI to basically fill these gaps and better understand how sea ice thickness changes on these short time scales. So this is what we would get if we looked at sea ice thickness observations on one day. We can use actually techniques to combine observations from different satellite sensors to improve the coverage, and then using information how thickness observations change in space and time gives us more understanding or more coverage. And then we can use AI to basically fill the gaps. So we kind of go from really sparse observations on one day to complete reconstructed maps of, in this case, freeboard, but effectively thickness on a given day. And lastly, I just want to kind of touch on some other areas some colleagues are working on over in Europe, really developing Earth observation data sets over sea ice. Now, new data sets relating to sea ice roughness, so how the kind of surface topography of the sea ice is changing over high resolution, like 1 kilometer scales, maps of melt ponds on sea ice at high resolution, and also new efforts in kind of downscaling, this idea that we can take a coarse resolution image and then we can downscaling is always counterintuitive to me, but effectively make it a high resolution image, and this is an example showing how they can do that based on Sentinel-2 data. Yeah, so I'm excited to see how we can leverage these new data to hopefully learn new things about what errors we have in our climate models and improve our the representation of these processes within our models. So just to kind of come back to where we started, AI is really making advances in our ability to predict sea ice on different timescales, both from data-driven models without representation of physics, these pure AI models making improvements in seasonal forecasts, but also in our ability to improve climate models in this hybrid modeling paradigm. So I'd be curious to know, what are people's thoughts on where we should be focusing? I think we're always framing sea ice prediction in this context as, it's useful for stakeholders and people who shipping for shipping routes and so on. But ultimately, I don't know anyone that's using these forecasts that we, for example, submit to SIPN every year. These are relatively coarse resolution forecasts, and would it be better if we focused our efforts on regional scale, higher resolution, and shorter timescale like nowcasting and so on? And good observational data, we can use AI now to really learn and extract new features of sea ice from things like altimetry and optical imagery and so on. And yeah, I think some of the challenges with that are, getting people access to these data. I know that some of my colleagues are developing these data sets, but we really need to start creating platforms where people can really interact and engage with these data. And I think that's one of the challenges there. But I'm about out of time, so I think I'll stop there. Take any questions.
Great, thank you very much, Will. Do we have any clarification questions for Will? Okay, so I think we'll open now for the more general discussion. And I'm going to take my prerogative as a moderator to ask a question, which for both of you, but we'll start with Will. So or do you have any concerns about using AI for Arctic research given the rapid changes in the Arctic? And kind of back to that question in the intro of whether, AI can extrapolate beyond, things it's currently seeing.
Yeah, that's something we've been thinking about throughout the entire lifetime of our project. This question of generalization to past and future climates has always had us worried, and that's something we thought we've got to think about at some point. I think there are definitely cool techniques coming out where we can do certain treatments to the input data to make things generalize better, like non-dimensionalization of input variables. And I think for the sea ice problem, the result I showed where I ran a 1-year forecast in the coupled climate model, I just did a test where I run a scenario up to 2060, I think, with that approach, and it was actually doing relatively well. It didn't go crazy and crash the model or run off. And I think for the sea ice is a kind of a particularly unique problem compared to the other components of the
kind of bounded.
Yeah, exactly. So, and the huge seasonal cycle that sea ice goes through every year, I think when you're training an AI model and that, it sees ice-free conditions in certain regions, especially if your model is constructed to make local predictions. It knows what ice-free conditions look like and what the kind of ice and ocean conditions are that facilitate ice-free conditions. So I haven't seen when I run it forward to 2060, it does go ice-free, but as in a physically reasonable way in line with the kind of ordinary model. So, and it doesn't go crazy. So that gives me hope.
Good. Okay, any questions? Gia, go ahead.
Yes, I think for seasonal, for annual, for 1 year's prediction, that okay because you have enough sampling and database. But for interannual and also decadal prediction using AI model, you still have some of the climate forcing, for example, internal variability and anthropogenic forcing. And I'd like to know how do you deal with it even you are not done yet? So do you have any idea how to deal with it? For example, climate model, you have 100 years handcast and another 100 years projection. And how, for the handcast part, how can you use the climate to consider internal and external forcing in the AI model?
Is that a question for me?
For both of you.
I can kind of jump in a bit there. I think it's really difficult, and ultimately the more data we have, the better we can kind of constrain this. And I think the passive microwave observations for sea ice have been really great. That's given us 45 plus years to train AI models with that have a really strong climate change signal in them. And there are other data sets as well which can help with that and other components. But you're right. I think from what I've seen in other approaches, some colleagues who are developing these AI emulators of climate components, and looking how they generalize under different warming scenarios, have generally found that if they want to be able to use these to answer climate questions that we have traditionally done with numerical models, like what does the atmosphere look like if I do an abrupt 4 times CO2 experiment and so on, and what if I do this prediction scenario, this one, and invariably they find that in order to get the better generalization, they have to train on data generated from the original model. But I think it's tough, and I don't think I have a great answer for it, but I think there are certain, as I was saying before, like certain techniques we can do to better handle or better treat the input data that we're giving it in terms of normalization and non-dimensionalization to make it more robust to traditional out of distribution, out of sample problems. But yeah, I don't know if Wen has any more on that.
Thank you. And
for detail,
did you have any thoughts on that, WenWen?
Yes, excuse me, I have additional. For the detail, when you train a model for 100 years, for example, do you input the temperature, surface air temperature into the model, and wind, and sea level pressure, and this kind of the external forcing?
Yeah, in our AI models, we have like surface temperature, basically mainly anomalies, surface temperature, air temperature, and also wind, U wind, V wind, and like a wind at different pressure levels. So in our paper, you can see a list of variables like the forcing that we have been put, and also the past 12 months of historical sea ice concentration data. So those are all like we consider important information for making the prediction with AI.
Great,
Okay,
thank you. So I'll just note one comment from the chat and then I'll go to you, David. So in the chat, Bjorn notes that he thinks the highest potential is in physics-aware AI and neural network modeling, where you bring in the physics of the ice mechanics. So any thoughts there on the more physics coupled models?
Yeah, I think there's a lot of people working on that in terms of how can we extract new physics from these machine learning models. And I think people have made pretty good advancements in that by using these techniques like equation discovery, where they'll I've seen it more in the context of the ocean. They'll develop for example, a neural network to represent some process like vertical diffusivity in the ocean, and then they'll do that with a neural network, and they'll see if they can kind of get the same performance using equation discovery, which is basically you throw in a bunch of different kind of mathematical operations and some terms, and it will kind of devise a new equation to represent that problem. And that kind of gets us more towards what we were originally working with in climate models, which is equations at the end of the day, and they're inherently going to generalize better than a neural network. So I think those problems or that sort of approach is difficult. I think it takes a lot of kind of manual tweaking to get that technique working. But there's also areas. I think there was out of Stanford. I think they've done some work on physics-informed neural networks to uncover kind of viscosity parameters in ice shelves. I think I would say check that out if you're interested. I think those are great techniques, and I think in a lot of cases it depends on, do I have the right data, and do I have the right, if I'm incorporating physics into the equation, or actual equations into my loss function, do I have the the right data in terms of is it going to be an under constraint problem, for example? I think they had a good case for their ice shelf problem, but
Great, thank you. David, go ahead.
Hi. So first off, thank you so much for the excellent presentations. Really appreciate it. Thanks also to my MOMP team members for keeping the ball rolling while I was out of the office for a while, and putting together this great session. I wanted to ask a question as an in situ observer. You've mentioned most of the talks have focused primarily on satellite obs. What is the role of in situ observations? And William, specifically, you mentioned that it was about the quality of the observations. What is if you had your druthers and a choice of the type of sea ice observations that we put out into the ocean, what would those be? And that's for both of you. Thank you.
Yeah. WenWen, do you want to start?
Yeah, so I think this is a very important question. Like, we rely on satellite image quite a bit because it's vast availability. Field measurement is important, but they are very sparse. So one way that we can integrate field observation into the model is to set them as a constraint. So once the model learned from larger amount of like satellite imagery, can they also satisfy these sparse and discrete observations? If not, so we can further constrain our model in order to match those field observations. So that is like one way to go from my research experience.
Yeah, interesting. Thank you. Well, any other thoughts on that?
yeah, I would echo those same points. I think they do have utility, even just as standalone data sets to learn new things about climate models. There's a study that came out from Lorenzo Zampiri and Marika Holland maybe a year or two ago, where they used mosaic data to try and learn something new about representing conductive heat fluxes through sea ice in large scale sea ice models. So I think has inherent challenges. How do you kind of translate a local measurement to a potentially 1 degree climate model grid box? But they found some really promising results in their case, and I think they went about it through a machine learning problem at first, thinking, can we like learn some correction to the conductive heat flux through the model? But I think they found they just had a great result with a linear regression for that problem, and got it to work really well. So I think in situ observations inherently have a great role to play, and I think more campaigns like Mosaic will really help us improve these representations of these processes in models.
Great. Well, the rest of you are thinking of more questions. I had a question for WenWen about the permafrost slumping. So I might have missed it, but what were the scale of those features that you were seeing, and kind of how small or how big of a feature does it have to be for you to be able to detect it?
That's a great question. From what our research is doing, a lot of these features are quite small. Like they are like in a few meters to several dozen meters in diameter. So there are a lot of large scale features that we haven't looked at yet. So in order to detect the small features, because small feature detection is challenging, and we need like high resolution satellite imageries in order to capture the details of it. So right now we are using the 2-meter resolution Maxar imagery, but when we are using like Sentinel-2, for example, it's 10-meter, a lot of the details will not be captured that well. So it really depends. Like for small feature detection, it's super important that you have the level of resolution of imagery for doing that. And at the same time, we are also experimenting a new thing. Like we know Sentinel-2 imageries are largely available and it's a long sequence of data. Can we make like some image super resolution in order to make the model to capture, like generating a high resolution from the imagery, from the open imagery we have, and then to apply it to a pan-Arctic scale mapping of those small scale features. So those are actually another direction we are exploring.
Great, yeah, that would be very cool. Gia, you have another question?
Yeah, one thing in statistics, when the ice cover, like ice concentrations is 100%. Most of them are in the Central Arctic. They are not random, nor independent. And usually in our statistics, we cannot use this for the analysis. And all the variability occur on the ice edge. And how about AI, deep machine learning deal with this issue? You still use like 100% observation to, well, to generate your AI model, or what kind of a tool, how to avoid this situation?
Do you want to take that
Asking
one?
hard
Wenwen?
questions, I think.
To
ahead,
both
Will.
of you. The reason is when I did Arctic, I like the first presenter, WenWen, and I separate the ice area into 7, 8 area, and I calculate the area, and then area is random and also independent. So I can use statistics and also can use a regression model to predict it. So when you use the spatial single value is not independent nor random.
Yeah, so I think the problem you mentioned is a spatial autocorrelation. So when we solve the continuous scale problems, we don't want to treat them as a discrete, like a point-based problem. Otherwise, we will lose this inherent spatial autocorrelation within the dataset. A good thing about the deep learning models is it can actually analyze the data in a continuous scale, capturing the spatial autocorrelation. But whether it can capture the physics under it, that is not 100% sure yet, because explainable AI is always been very challenging goal to achieve.
Okay, and I wanted to again remind folks of the Google document and maybe ask Jingyi, do you want to say something about the comment you put in the Google document about your soil data set?
Yes, thank you. So we are actually looking for ground-based observations to train AI models. So I think similar issues for CIs and other things. So when it comes to the ground-based measurement, so it's really limited, especially in the Arctic region, in Alaska and other regions. So I just want to maybe open for more broader comments to see for the whole community. Do you feel like AI can be used to assist in sampling design to make the ground survey more efficient, or do we still need more ground data for the AI models?
I'm guessing everyone thinks we need more data for the AI models, but there's also a question in the chat asking if you integrate indigenous or local people knowledge as input, or whether your data is just limited to satellite data. So that might be also a question of how could you integrate indigenous local knowledge?
Yeah, I will try to answer this. I think indigenous knowledge, like the local observations, is very important because it gives us the first-hand observations view about the environment. So in the Arctic, like especially in the permafrost, there is the Li network, the local observer environmental network. So they have include a lot of this local news reporting observers see the abnormal environmental change or the animal changes. So what we are currently experimenting is from this local news, they have text descriptions, and then we have the large-scale environmental monitoring. How we can integrate, these are real multimodal data because we have text, we have photos taken at the community level, and then we have the large-scale physical observations. So one way of integrating this multimodal data is at the embedding level. Like after we convert original raw data into some representations that deep learning is good at processing, and then we can integrate this kind of local scale knowledge with large scale, like global or regional scale knowledge. That I think will be a very cool attempt for the community.
Yeah, that would be great to see that different types of knowledge integrated. It's challenging, but would be really exciting. Okay, we are at the top of the hour, so I want to thank our speakers again. That was both really great presentations, and it's been really good discussion. Hazel, did you have any wrap up? I don't seem to have lost Hazel.
I'm right here.
There you
Yeah. I just put a link in the chat for where you'll be able to find the recording. Feel free to share that around. Yes, thank you again to our wonderful speakers. And I think if you haven't already joined IRPIC collaborations, please do that to stay up to date on our next meeting series. There's a couple of interesting ideas coming up, including, I believe this in a month or two, we'll be hosting a meeting to specifically talk about the Arctic Research Plan and gather input from the community, and would love to see you all there and see how maybe we could pull some of this discussion into ideas for the Arctic Research Plan. So thank you all very much. That's all from me.
Thank you all. Have a great afternoon.
Thank you, everyone.